Okay, so we are back again, right? So particularly now next example we will take, it is a if you see that it's a voltage source of 10 sin pi t volt, right? Now this time varying voltage for current function we will see in the your AC circuit analysis, single phase and three phase, but just to give us some kind of ideas, right. So 100 sin pi 10 sin pi t volt is connected across a 5 ohm resistor. We have to determine the current through the resistor and the power dissipated. So we know I is equal to V by R. So voltage is given 10 sin pi by t. So and R is 5 ohm, it is given, R is 5 ohm, it is given, right. So that is actually 2 sin pi by t ampere, it is a time function. So and power is equal to V into I. So it will be voltage is 10 sin pi t into 2 sin pi t. So ultimately P is equal to 2 sin square pi t volt. It is a time function, but in the case of single phase AC circuit or three phase AC circuit, when we will go for AC circuit analysis, at that time we will see this one, right. So next is that nodes, branches and the loops, right. These three things now we have to try to understand little bit. So the elements of an electric circuit can be interconnected in several ways, because we have electrical circuit, there are maybe elements or devices. The convention when addressing network topology is to use the word network rather than the circuit. So we may regard a network as an interconnection of elements or devices, whereas a circuit is a network with one or more closed path that I have underlined for you, right. So we need to understand some basic concept of network topology. In network topology, we have to study the geometric configuration of the network and the placement of the elements in the network. So these elements include branches, nodes and loops. Now suppose for the purpose of explanation, suppose this is a figure, that is nodes, branches and loops we have to find out. Now look, all write up is there, but just see that how things are. So if you look at this diagram, that this one, or what, just let me mark it. So this one, this point and this point, these are all 3 points, they are connected, your what you call by wire. So wire has negligible resistance, but there is no element, electrical element in between these points, right. So how many elements are there? 1 2 volt source, then 5 ohm resistor, 3 ohm resistor, 6 ohm resistor and 2 ampere current source. So there are 5 elements, right, electrical elements in this circuit. So and here also these are all connection of wire, and wire has negligible resistance. So in that case what we can do is that how many branches and your what nodes, branches and loops are there. So then generally any electrical element, it is connected across 2 points or 2 nodes, right, we will come to that, across 2 terminal. So that means that is a branch. That means this voltage is also connected across 2 terminals, so it is a branch. This 5 ohm resistor also connected across here and it is a branch. Similarly 3 ohm also connected across these two, it is a branch. So 6 ohm also connected across the terminal, it is a branch, and the current source also connected across this is a branch, right. So in this, that means, and this all these 3 nodes, all these 3 points, they are connected by what you call by wire, and these 4 points 1 2 3 4, these 4 points also connected by wire, right. So this can be clubbed together because wire has negligible resistance. So these 3 points can be clubbed together, and this your all 4 points can be clubbed together. So that means nodes should be here. This is one node A. This all these 3, if we club together, it will be B. That's why it is I brought them inside the your dashed dashed portion. This thing, this 1 2 3, and here also I have your encircle them, that all the 4 points together. So that means this is one node. If you club together all these 3, it will be another node, and if you club all these 4 together, it will be another node. So there will be 3 nodes. That means your equivalent one, if you see this, just hold on, right. If you see this equivalent one, so this is my equivalent one, because all these 3 nodes clubbed together, all these 3 nodes, these all point club together, these 4 also club together because they are wire only. So, finally, its equivalent one is your what you call this A, B, C. There are 3 nodes and 5 branches, one voltage source, this 5 ohm resistor, this 3 ohm resistor, this 6 ohm resistor, and this 2 ampere your current source, right. So, therefore, generally your what you call the branch represent a single element that I told you, such as voltage source or a current source or a resistor for the in the case of this your what you call that DC circuit, right. So, usually node is indicated by a dot in a circuit, that is your this all dot is indicated your by this thing, node is indicated by dot, right. So, if a connecting wire, that is I told you, connects 2 nodes, the 2 nodes constitute a single node because wire has negligible resistance, that is why this has been clubbed together and all these things have been clubbed together, right. So, therefore, we have 3 nodes in this circuit, therefore, we have 1, 2, 3 nodes in this circuit and you have 1, 2, 3, 4, 5 branches, right. So, this your what you call, so figure 9 shows the simple, this is figure 9. So, now question is that means a node is the point of connection between 2 or more branches. So, if you take this is a node, say node B, it is at least 2 or more branches connected here. If you take point A, at least 2 branches are connected, and if you take here that more than at least 2 or more branches are connected, right. That is called a node, right. Therefore, a node is the point of connection between 2 or more branches. Now a loop in the electrical circuit, before explaining the before telling this, a loop means, suppose if we start from here, start from this point A, say if I take suppose I am starting from this point A. So, if I move like this, and if I move like this A to B, say 6 ohm resistor, and if I move like this and coming back to the A, so A B C A, so A B C A, this is a loop, right. If I move like this, suppose I am moving like this, clockwise or anti-clockwise, say I am moving clockwise, So, in this case A B C A, it is a loop, right. So, question is that you have to find out the independent loop. Now, what is just 1 minute, let me clear it, right. So, question is that you have to, so if you try to find out that how many loops are there in this particular circuit, the figure 2.9, this you will find 6 loops, but 3 of them are independent loop. Now, question is that what is your independent loop, right. So, that I told you that your what you call that closed path containing 3 ohm resistor is a loop, right, A B C A. Similarly, here you can get another loop, you can get another your just hold on, you can get another loop. Suppose this is if you move like this and come back here, right, I am moving like this and coming back like this. So, this is another loop, this is also A B C A, but you have A to B, you have your 5 ohm resistor is there, then B to C, I am taking this 3 ohm resistance, then B to C you have 3 ohm resistance, then going to C to A, that is your 2 volt source, right. So, 5 ohm, 3 ohm and 2 volt, this is also a loop, So, this way you will find, just one more, let me clear it, right. So, this way in this circuit you may find there are your what you call 6 such loops, but only 3 loops are independent, just hold on, right. So, question is that a loop is said to be independent, just I am underlining for you, a loop is said to be independent if it contains at least one branch which is not a part of any other independent loop. That means, a loop is said to be independent, right, if it contains at least one branch will be there which is not a part of any other other independent loop, at least one branch should be there which cannot be part of the other independent loop, although you will get 6 loops, but only 3 loops will be independent. So, in this circuit your just a minute. So, let me clean this one, right. So, in this circuit just hold on. So, in this circuit that I can mark two independent loop. One is A B C A, that is 5 ohm, 6 ohm and your 2 volt source. This is one independent loop. Another one I can say A B C A, that is 5 ohm, 2 ampere current source and 2 volt. So, these two independent loops I am telling, but one more is there, although 6 will get, the third one is an exercise for you. So, one independent loop I am telling, say A B, say this one A B C A, for example say 5 ohm, 3 ohm and 2 volt. I am making it for you, just hold on. Right, one is say A B C A, that is A to B. If you take A to B, this is 5 ohm resistance, then you can take B to C, this path 3 ohm resistance, and C to A, this is your 2 volt, right. This is one your what you call that one independent loop. Another one I can take again A B C A, say A to B, that is 5 ohm, then B to your what you call B to C, that 2 ampere current source, right, and then C to A again your what you call that 2 volt. So, if you look into that, you will find that at least one branch is your what you call not common to others, but one more is there, one more independent loop is there. So, it is an exercise for you to find it out, right. So, let me clean it. Right. So, that means in general, so here also everything is written, the two independent loop I have mentioned here, right, but third one you have to find out, very simple it is, slowly you will know, right. So, now in a network, if you have n number of nodes, and L number of your what you call independent loop and B number of branches, the relationship branch is equal to L plus n minus 1, right. So, this relationship B will be L plus n minus 1, that means other way if I write here that L is equal to, that is your independent loop is equal to, it will be B minus n plus, from this equation only, L is equal to your B minus n plus 1, right, this is plus 1, right. That means if you know the number of branches, suppose B is known, then your number of branches are known, then if you know the number of nodes, then you can easily find out how many will be your independent loop. So, let me clean it. Right. So, this is equation 12, it is actually topic 2, chapter 2. So, it is 12, right. So, that means easily you can find out that your what you call that everything is written here, right, all these things, and when elements are connected sequentially, so there will be series, and when they I mean when you will say that when that elements are in series means through all the elements that all same current is flowing, and when it is in parallel means it is across two terminals, that means across those elements the voltage will remain same. So, this is the your what you call this relationship B is equal to L plus n minus 1. So, for example, so determine here, this is a circuit is given, you have to find out that number of branches and nodes in the circuit shown in figure 2.10, right, and also identify which elements are in series and which are in parallel. So, question is that if you, this is a simple problem, you have to find out that your number of your what you call branches and nodes in the circuit, and which elements are in series and which elements are in parallel. So, if you look into that, this point, these three things, I mean I will go to that this is actually connected by wire, I mean these 2 points connected by wire. So, nodes we are marking it by dot. So, this is basically one node because it is wire only. So, it clubbed together, and similarly here also 3 points we are marking. So, they are clubbed together, right. So, this is A node and this is another one, that is your B node, right. This is another one because any electrical elements your connected across across two terminal means this is a branch. So, this is a branch, and from this is clubbed together. So, from this A to B is another branch because it is a single point, and similarly here to here it is another branch because it is A to C, because all these are common points. So, A to C, and similarly A to C another 2 ampere current source is there. So, if you come to the equivalent circuit, so when you club together, then this point is a this is clubbed together. So, this point, it is understandable. Then these 3 points are clubbed together because they are simple wire only, right. So, they are negligible resistance. So, we do not consider them in the circuit analysis, we neglect them. So, all these things are clubbed together, that means this is a point C, and finally, this is the equivalent circuit. I mean, what exactly we want. So, there are 3 nodes A, B, C, and how many branches are there? 1, 2, this is a current source, it is connected across a terminal AC, a 4 ohm resistance also connected across your AC, right, and 8 ohm resistors connected across AB, and this 40 volt your voltage source is connected across BC. So, there are 2 ampere current source, 4 ampere resistor, 8 ampere resistor, and 40 volt that voltage source. These are the 4 elements and 3 nodes, and series or parallel, this current source connected across AB, 4 ohm resistor also connected across AB, that means they are in parallel, and this 8 ohm resistance and this voltage, they are connected in series. That means across AB voltage will remain across AB, that across 4 ohm resistance, whatever may be the voltage, across 2 ampere current source will be the same voltage, because they are connected across the same terminal. So, they are in parallel, and this is same current will flow to 8 ohm as well as 40 volt source, because it is a 48 ohm and 40 volt are in series. This is the idea. So, from this problem, you first mark it like this, right. I mean, we are neglecting wire, so wire resistance cannot be considered in circuit analysis. So, club together, finally circuit will look like that, and it will be easy for you to solve the circuit, right. So, this another problem we take, this is a example 6. So, here also this is another circuit. So, determine the branches and nodes of this figure 13, right. For example, to also identify the elements that are in series or in parallel. So, here also if you look that this point and this point, this is wire only. So, and this can be clubbed together. Here also it is wire only, this can be clubbed together, right. I mean here it is shown, look, this is wire only, it can be clubbed together. So, here and here these 2 points clubbed together. So, mark it by a point only node. So, this is a node 1, and similarly here also if you see this point also can be your these 2 points clubbed together. So, it is also encircled, these 2 points clubbed together, and these are all wires 1, 2, 3, 4. These 4 points are clubbed together, these 4 points are clubbed together, right. So, it will be easy for you to solve the circuit. So, in this case what will happen? So, everything is written here, So, you have 6 ohm, how many electrical branches are there? 6 ohm, then 20 volt, then 2 ohm resistor, then 4 ohm resistor, and 9 ohm. Altogether you have 1, 2, 3, 4, 5. You have 5 branches. So, all these things are written here, and how many nodes are there? This, if you club together, it is 1 node. If you club together, node 2. If you club all this together, node 3, right. So, this is altogether 3 nodes and 5 branches. So, not simplified further. Here the way we have made it, you can also now make like the previous example circuit, you can make this one also, right. So, next so this is very simple thing, this is understandable for you. Now, next is that your what you call Kirchhoff's laws. Actually, he was a German, and generally in the pronunciation, whatever I have understood from the people who actually in this thing. So, actually the C should remain silent in pronunciation, it will be Kirchhoff's laws, right. So, C should remain silent. So, anyway, so Ohm's law, actually now we will come to the Kirchhoff's law. There are 2 laws, first law and second law, right. Now, Ohm's law actually is not sufficient to analyze the circuit. However, we can analyze a large variety of electric circuits if Ohm's law is coupled with Kirchhoff's 2 laws, right. So, actually Kirchhoff's laws are first introduced in 1847, right, by the German physicist Gustav Robert Kirchhoff. Lifespan was 1824 to 1887. So, these two laws are actually formally known as Kirchhoff's current law, that is KCL, and Kirchhoff's voltage law, that is your KVL. So, Kirchhoff's first law is based on the law of conservation of charge, right. So, this is a very simple thing. Since I am underlined, let me underline for you, right. It is basically it is a conservation of charge. So, since conservation of charge postulate that, earlier also we have discussed about this, that the charge is neither created, it is neither created nor destroyed. The charge which enters a node in a network must either leave instantaneously or be stored there, right. But however, it cannot be stored because the node is an infinitesimal mathematical point, because the node is an infinitesimal your mathematical point, right. And just hold on, let me clean this one, right. So, so charge actually possesses a finite mass and size. So, hence the charge which arrives at a node at any instant must leave immediately, because node actually mathematical point is, I mean, infinitesimal small, very small point, right. And charge actually possesses finite mass and size, and the charge which arrive at any node at any instant must leave immediately, right. So, in terms of your currents, the total current entering a node must be equal to the total current leaving the node. So, Kirchhoff's first law is coming from the your what you call that your conservation of charge. So, for example, therefore, the KCL, that is Kirchhoff's current law, states that the algebraic sum of currents entering a node is equal to 0. So, mathematically the KCL can be written as, say, sigma k is equal to 1 to n I k is equal to 0. This is equation 13. This is mathematical, where n is the number of branches connected to the node and I k is the kth current entering or leaving the node. Suppose you have at particular node, suppose there are 5 branches are connected. So, current entering or leaving the node, the algebraic sum is equal to 0. So, for example, if you take this your what you call this diagram. So, in this case only one node is there. If you see how many incoming current, look, I3 and I4 are, and I1, I3, I4, this is incoming current, and I2 and I5 are outgoing current. Therefore, if you apply KCL, the KCL at this node, that is Kirchhoff's first law, current law, if you apply at this point, then applying KCL, it gives because algebraic sum your what you call of the current meeting at this node is 0, right. Therefore, if you apply, say, if we take that I1, I3 all incoming current is your positive sign, then I1, then minus I2 because it is outgoing, I1 minus I2 it is incoming, then plus I3 it is incoming, plus I4, and it is your outgoing, minus I5 is equal to 0. That means, if you look I1, then I am algebraic sum, that is why I am putting plus, then in bracket I am writing minus I2 plus I3 plus I4, because these two are I3 and I4 are incoming current and I5 is outgoing current. So, plus in bracket minus I5 is equal to 0. Since currents I1, I3, I4 are entering the node, while currents I2 and I5 are leaving the node. In other way you can write, if you rearrange this, that incoming current I1 plus I3 plus I4 is equal to outgoing current I2 plus I5. This is equation 5. That means, that any node in sum of the incoming current is equal to the sum of the outgoing current, that is your KCL. Therefore, this is an alternative one, but same thing, but it is easiest one, right. So, it is clear that sum of the current entering a node is equal to the sum of the currents leaving the node, right. Then Kirchhoff's second law actually is based on the principle of conservation of energy. First one was conservation of charge, second one is the principle of conservation of energy. Suppose in a gravitational field, the energy level of a point with respect to point 2 can be found by moving a unit mass from point 1 to 2 and noting that the energy given up in the process, right. That is from the physics. Now, similarly, in an electric circuit, the energy level at point 1 with respect to point 2, I am just underlining for you, right. Similarly, in electric circuit, the energy level of point 1 with respect to point 2 can be obtained by moving a charge from point 1 to 2 and noting that the energy given up in the process, right. So, the energy that is energy actually that due to 1 coulomb charge gives up as it moves from point 1 to point 2, that is gives up as it moves from point 1 to point 2 as in the same as the same along any path from 1 to 2. It is whatever way you take, right. So, that means you are taking a Coulomb charge from point 1 to 2. You are noting that what is the energy given up. So, let me clean this. So, since the energy lost by a Coulomb charge, right, in moving from, again I am marking for you, since the energy lost by Coulomb moving from point 1 to point 2 is independent of the path. So, the energy for any round trip must be equal to 0, right. This is actually from the conservation of energy. Now, the Kirchhoff, just a minute, let me clean it, right. So, just hold on, let me clean it. Therefore, the second law, the Kirchhoff's voltage law, that is KVL we call, states that the algebraic sum of all voltages around a closed path or loop is equal to 0, right. This is KCL, first law was KCL, right, and second one is Kirchhoff's voltage law, that is KVL. It states that the algebraic sum of the voltage around a closed path is equal to 0. Now, mathematically the KVL can be expressed as a sigma P is equal to 1 to m, say Vp is equal to 0, where m is the number of voltages in the loop, later we will know, right, or the number of branches in the loop, right, and Vp is the pth voltage. Now, if you look for the purpose of explanation of the KVL, if you look into this circuit. So, here what we will do, we will follow certain convention. So, write up is there, but suppose this is a circuit, this is a voltage source, it is plus minus, it is a your what you call plus minus polarity is shown, and this resistor also plus minus polarity is shown, here also resistor plus minus polarity is shown, and this is also V4 plus minus polarity is shown, but we have to follow certain your what you call certain convention. Now, in this case, whenever that your current, this we have to follow certain convention. So, arbitrarily we have marked plus minus whatever voltage of polarity you know, mark it, resistor also arbitrarily you mark, it does not matter. Ultimately, when you will solve using your Ohm's law and your Kirchhoff's first law and second law, you will get the same solution. So, in this case arbitrarily you mark, then what you do when current entering into the positive terminal, suppose this current is, suppose this is that current is, you have taken the direction in the anti-clockwise, clockwise direction, and this is suppose this way, suppose we are moving it or moving it clockwise, this is actually we are taken that we are moving from the clockwise. So, as soon as you move from the clockwise, you see which terminal you are first encountering. So, as you are moving from the clockwise, so first you are encountering the negative sign. So, it should be minus V1. Now, as you are moving like this clockwise, encountering first the plus terminal, we have taken arbitrary, say, right. So, this is your plus V2. Then again when you are coming entering this, you are considering this one. So, this same we are moving clockwise. So, encountering the plus terminal first, it will be plus V3. Then when you are moving clockwise, so encountering the minus sign, so minus V4, right. And then when you are coming to here clockwise, this way I have shown, but for your understanding I am making the path. So, minus, this is actually minus V5 is equal to 0. So, minus V1 plus V2 plus V3 minus V4 minus V5 is equal to 0. Otherwise, V2 plus V3 is equal to your V1 plus V4 plus V5, right. This is the thing, because we have marked polarity, but you move, if you are moving clockwise, see first which polarity you are encountering first. So, voltage case, if you move like this, first minus, so minus V1, here it is plus V2, encountering plus V3 minus V4, then your minus V5 is equal to 0, right. So, let me now clean this one. Right. So, the same thing I have written here for you, all this write up is there, but same thing, that minus V1 plus V2 plus V3, what I have written here, this is equal to 17, or rearranging the term V2 plus V3 is equal to V1 plus V4 plus V5, that is equation your 18 may be interpreted as sum of the voltage drop is equal to the sum of the voltage rises, right. So, this is that means sum of the your what you call voltage drops, that is V 2 plus V 3, right. That is V 2 V 3, there will be voltage drop across the resistor, right, as per this thing, and this is an electrical element. So, it is not a resistor, maybe something else, right, is equal to your sum of the voltage rise, whatever polarity we have taken, all this is voltage drop and other things voltage rise. So, this one may be interpreted as sum of the voltage drop is equal to the sum of the voltage rises. So, it is an alternative form of the KVL, that is the Kirchhoff's second law. So, note that if we had travel counterclockwise, the result will have the same, right. Suppose if you move, we have moved clockwise, you can move anti-clockwise also, result will be same. Just I am showing for your the way you want. Suppose same circuit, although if you move, this is clockwise, if you move anti-clockwise like this, if you move anti-clockwise like this, so I am moving it. So, as anti-clockwise if I move, so this is ultimately you will get same thing, this is V 1, right, you move like this, this is plus V 5 because it is encountering plus terminal, here also plus terminal pass, this is also encountering plus terminal because we are moving like this, we are moving like this. So, this will be your plus V 4, then we are moving like this, so encountering minus sign first, so minus V 3, and here also encountering minus sign first, minus V 2 is equal to 0. That means, your same thing you got V 2 plus V 3 is equal to V 1 plus V 5 plus V 4, whatever we got. So, let me clean it. So, clockwise or anti-clockwise does not matter, you will get the same equations, identical thing, right. So, your what you call anti-clockwise I not shown here, but I told you the same thing, V 2 plus V 3 is equal to V 1 plus V 4 plus V 5, right. So, suppose if we take another one, suppose this figure 2.17 voltage sources in series and equivalent circuit. Suppose if we take that this particular your circuit, that we have 3 voltage sources, right, V 1, V 2, V 3, and this is another is there, one more is there, this is V 4. Now, if you add the your what you call the total voltage sources, if you move clockwise whatsoever, and this is your voltage VAB. If you move clockwise, say clock or anti-clockwise, it does not matter, you will get same thing. Suppose if we move like this, just hold on, if we move like this, suppose I am moving clockwise like this, So, what will happen if we look into that, the plus, as soon as clockwise moving, it is plus V 1, right, then again plus V 2 because it is clockwise, this is also clockwise, I am moving clockwise, this is plus V 3, this is V 2 plus V 3, then clockwise, this is minus V 4 because minus sign encountering first, minus V 4, then here also VAB is there, but I am moving clockwise, so encountering minus terminal first. So, minus your VAB is equal to 0. That means, VAB is equal to your this V 1, what is written here, then plus V 2, then plus V 3, and that is your VAB, right. So, VAB is equal to this one, VAB is equal, actually this is VAB, and Vs is source, actually is a supply voltage. So, VAB actually is equal to Vs. So, this way we can make. Now, if you apply here also your clockwise, that your KVL, it will be your Vs minus VAB is equal to 0. So, VAB is equal to Vs is equal to VAB. So, that is VAB is equal to V 1 plus V 2 plus V 3 minus V 4. I think everything is understandable to you. Thank you very much. We will be back again.